Hello everyone, and welcome to another lecture video for the course of database design and implementation. In the previous lecture video, we had basically discussed about the importance of a good database design. Okay. So in this topic, we had taken a specific example from the university problem domain and given a particular subdomain that was with regards to storing the students' personal information and the information about the courses that they're enrolled in, we tried to come up with the design of a particular database, right? And in doing so, we discussed an intuitive way of generating a database design and discussed some of the possible challenges that could be present if we do not follow the well-established techniques of database design that we are going to learn through the course of this semester. Okay. Thereafter, we had also talked about some basic terms and definitions. Okay. We had discussed about what do we understand by data, what do we understand by information, and then what do we understand by knowledge. We also introduced ourselves to some of the basic terminologies that are used for data storage purposes, right? So we discussed about what do we mean when we say a field, what do we mean by a record, what do we mean by a file, and so on and so forth. Okay, and we also discussed the equivalent terminologies of these terms within the database system environment. Okay. Then we talked about the evolution of data storage and processing, where specifically the topics that we learned about was the computerized file system, the challenges in computerized file systems. Okay? And we learned about the issues of data redundancy and then data anomalies, which were of three types, where you could have insertion anomaly, you could have update anomaly, and then you could have deletion anomaly. Okay, so some of these anomalies could be present due to the presence of data redundancy in particular, right? Whereas some other nature of these anomalies can be present due to the different ownership entities that was a criteria, or not a criteria, but a feature within the computerized file system environment. Okay, and we related or we discussed these anomalies with respect to the example of good database design, the importance of good database design that we were discussing previously before we came to these particular topics. Okay, and then we finally introduced ourselves to the database system environment. Okay, just a brief introduction. So there were some reading assignments after that, which was specifically about learning about the different components that you have in the database systems environment, as well as some of the functionalities of the database management systems. So if you have not done that yet, please make sure that you read that from your textbook because they will be necessary going forward. Okay. So in this lecture, the agenda of this lecture, of today's lecture, will be to understand what are data models and what is the process of data modeling. Okay. We will talk about what is this process and why it is important, okay, with respect to the overall process of database design. Okay. Then we will look at some of the basic building blocks of data models. So typically, just a quick peek into what data models are. Data models are basically a graphical representation of your database design that can be used to convey your ideas, and it can also be used to represent how end user data will be stored and processed, right, to different subdomains or different entities within your organization for whom you're developing the database, right? So in order to be able to show that graphical representation, you need certain terminologies or you need certain components. So that is what we mean by the basic building blocks of a data model, which is to say that what are the different components of a data model which will be used when we will be graphically representing our database design. Okay. Then we will talk about business rule, which are nothing but establishing the set of rules and constraints that will guide your database design. Okay. Of course, there will be some limits to what your database can and cannot do, right? So how do you get to that point, and how do you formally establish that? So what we are going to learn here within the realm of business rule is, once you fulfill or you get the client's requirements for your database design and the requirements from other entities or units from within your organization who will be interacting with your database, then you need to transform them to what is known as a set of business rules, okay, to establish the set of operationals or functional requirements, and then establishing the constraints of what can and cannot be done within your database, okay, or what type of data will be stored within your database, what will be the interaction between the different entities or different tables within the database that will be implemented, and so on and so forth. So once business rules are established, then along with the basic building blocks of the particular data model that you will be adopting, you will be able to basically come up with the graphical representation of your database design, which will be the blueprint of your database. Right? So that is the purpose of this particular topic. Thereafter, we will briefly discuss about the different components and functionalities of different data models that are available to us. So we will talk about the evolution of data models as well. So from where did we start and where we are right now, right? And which one is the most important one, which we are going to follow uh, over the duration of this course. Okay. And then finally, we will talk about a topic which is known as degrees of data abstraction. Okay. But in simpler terms, these are basically the steps that needs to be followed to design and implement your database That is what this is basically is, right? So we are going to see a bird's eye view of the different steps that needs to be followed in order to generate the design of your database and then implement it in a very structured fashion. Okay? So without further ado, let's take the first topic and let's understand what are data models and the technique of data modeling. Okay? So typically, the whole purpose of database design is to convey how end user data will be stored and managed. Okay, so that is the overall goal of a database design. And typically, data modeling is the first step towards generating a DB design. Okay. So then the question is, what does a data model represent? So a data model represents a simple graphical illustration of your DB design. So that is one of the primary objectives of a data model, right? And the second thing that a data model will represent is the functionality of your database. That is how your database will operate and interact. So in this particular instance, when we are talking about the operationality and the interaction of your database, there are two different perspectives that you need to consider here. Some of the operationality or the functionality is the interaction between the different tables that you will have within your database, right? And in technical terms, this is known as the relationship between these different entities, right? So that means if we want to put it into an example perspective, if you recall the example of the good database design that we were talking about, and if you had done the exercise where you had to redo that example by creating a better intuitive design than the simple one that we had discussed, then you will note that there are two contexts that were present there. So one context was the student's personal information. So that was the student context. And the second context that was there was the information about the courses. And there was an interaction between these two particular entities in the form of that student's registers for courses. So that is what we mean when we say that one of the perspectives of the interaction is between the entities or the tables that you're going to implement within the database itself. And the second perspective comes from the interaction of external users or internal users against your database itself. So when we say internal users, then we can mean that you have the database administrator who is capable of interacting with the database. You have database designers who are capable of interacting with the database. Then you also have application developers who are going to write programs and procedures which has some specific goals with respect to interacting with the database, right? Let's say with respect to generating analytics from the data that is being stored in your database. So those kind of interactions are internal interactions. And then you have external interactions, which is of course going to come from your organization's clients or customers, right? Or basically the end users who will be querying the database to get information out of it, right? So those kind of interactions and operations to a major extent can also be represented by using this graphical illustration of your database design. That is by using the aid of your database model. So along with the way your database functions, you can also represent the different relationships or different objects, properties, relationships, and constraints of your database design. Okay, so that is the overall importance of a data model. Okay, so we need to have a database design. That is the absolute necessary step towards implementing a database. And data modeling helps us to generate the database design by providing us with tools and techniques which will be able to help us generate a graphical illustration of the database, express its functionality, that is the way in which the database operates, and its interaction between different components and the external and internal users, and then the different objects, properties, and relationship or constraints that you want to enforce within your database design as well. So one thing, a remark on data modeling is that it is an iterative process. So what that means is that similar to how you design algorithms, okay, for your typical software projects, you cannot necessarily expect your data model to be completely perfect from the get-go. So there might be a requirement later on during the stage of your database design that you might have to come back and modify some of the aspects of your database design, right? So the reason why it can happen is that the end user requirements or client requirements might change over time. Okay, not like over time, but separation of it. Then organizations requirements might also change over time, right? Then also you might change some of the vendors that is used to implement your database. You have to keep in mind that current generation databases are vendor reliant. Okay, so it could be Oracle, it could be IBM, it could be even Google, Amazon, so on and so forth. So each of these vendors has their own tools and techniques that they provide or they ship along with their database management system. okay, or database management software. So if you change those vendors, then the capabilities that you had previously might not be the same. You might have some added benefits, or you might have some added disadvantages by getting some benefits in some different areas. If that happens, then you might have to revisit your design in order to kind of iteratively change some of the aspects of your design representations. Right? So always keep in mind that whatever model or design of your database that you generate, which will be a representation of your database itself, like, so it's like the algorithm for your database. You might have to revisit it and you might have to change it. And that is the reason why your project is set up in 3 phases, is because you can then come back based on the feedbacks that you receive to change your database design and improve it, right? So that is what you have to keep in mind. The second remark that we have along the process of data modeling is what is an appropriate data model. So now if you ask yourselves the same question, because since you can understand that there is some kind of correlation between the nature of writing algorithms for programs and then performing data modeling for implementation of databases, if this same question is asked to you in the realm of programming, that what is a right algorithm, what is going to be your answer, right? So in that domain, you would say that, okay, first of all, it is capable of accepting the specified inputs, the algorithm. And then for those given inputs, it is capable of generating the required outputs correctly, right? It runs efficiently. The algorithm runs efficiently. That is, the time complexity is not that terrible. It runs correctly, it terminates, right? And the logic of the program that needs to be implemented is encapsulated within the context of the algorithm that you write or design, right? So that is what an appropriate algorithm is for any given program. So similar to that, now if you ask yourself that what is an appropriate data model, then your answer is not about saying that, okay, you need to have X amount of entities and there needs to be some certain types of relationships between those entities, and there should be certain nature of interaction between the end users or the internal users, and so on and so forth. So the first thing that you have to keep in mind, that if you are asking yourself what is the appropriate data model, then the first thing that you need to keep in mind is that it should describe end user data storage correctly. So whatever the data storage requirement is, that should be clearly described by the data model. Okay. Thereafter, we should be able to verify the integrity of the stored data using the data model itself, right? So that means whatever data you have stored, it is accurate, right? And at times minimizes data redundancy as much as possible, right? And you can also add a few more points to it and say that avoids null values. Okay. And later on, when we go to the specific model that we will use, we will also learn about two different rules that needs to be followed for every database design which will be generated using the relational model. That is the entity integrity rule, and you don't have to worry about it right now, but in the next chapter we will learn what it means. So the entity integrity and referential integrity must be preserved. Okay. So this is what the design of your data model should ensure as well, that these things are preserved. So thereafter, it should also allow us provide us with data manipulation techniques. So the goal of this data that you're storing is to be able to process it and manage it such that you can generate information from it, right? So if you're not able to manipulate the data that is being stored, then just storing the data is not giving you any added benefit. Because remember, as we discussed in the motivation of this course, when we were talking about the motivation, we mentioned the fact that the end goal for businesses to be able to store data in a structured and proper fashion is that they can run some analysis on it, get some information and results, and then make good business decisions on it that will help them in the long run, right? So that will require us in some way to transform the data that we have already stored, right, to generate the information. So that means in order to do that transformation, the data model should provide us with different data manipulation techniques which will be able to do that transformation. Okay, and in simpler terms, this relates to things like having SQL queries or being able to write transactions. Okay, so even these techniques are something that is provided to us by the data model that we select, right? We don't necessarily write how these techniques are implemented. We just use these techniques in order to specify what we want to do. And that is the difference between procedural language versus non-procedural language, where here, all of the techniques that we have fall in the category of non-procedural language. That is, you don't have to specify as the designer how do you want to do the transformation or what kind of techniques needs to be implemented in order to perform the transformation. All you need to specify is what transformation do you want, and then specify that or outline that by using the syntax of the non-procedural language. And then the data model provides you with the inbuilt techniques to kind of implement those transformations. Okay, so these are some of the essential uh, properties that should be present in the data model that you select, whichever that you end up selecting. So the remark number 3 is basically data models helps to act as a bridge between all involved parties. Okay, and all involved parties, when we meet this, we can have different entities, right? So we can have end users, then we can have different units within the organization, and then you can have programmers and app developers who will also want to use the database, right? And then you can have database designers and database admins. Okay, so what is important for us to pay attention to, that each of these different involved parties will have a different perspective of how the data needs to be stored, what data needs to be stored, and what kind of functions they want to perform on that data, right? So all of them have a different perspective, specifically relate to what data to store, what processing to perform. Okay. But if you remember, if this issue is implemented for each involved entity within our database design process, then it kind of takes us back to the file system domain, where all of the different involved parties will have their own version of the files, and that will lead to data redundancy and data anomalies, right? So, and what we want from a database system environment is that you can have, let's say, the different parties or the different units of your organization, and they will all interact through the database management system, the DBMS, and then the DBMS will interact with the database server, which will host all your data. Right? So in order to achieve that, these different perspectives that is coming from the different involved parties needs to be somehow merged together into a single view of your data, right? And the tool that helps us achieve that are data models. And that is the reason why data model is the first step towards any database design. We have to adopt a data model and then go forward with it. Okay. So now that we understand that, let's look at the next topic, which is the building blocks of a data model. Okay. So there are 4 basic building blocks of a data model that you can find across almost all the data models that is available to you, right? So what we will do is we are basically going to define what these different building blocks are and what do they represent. Okay. So first of all, I'm simply going to write them down and list them, so then we can go over them one by one. So the first one is known as entities. Okay. And then we have attributes. Thereafter, we have relationships. And then finally, we have constraints. Okay. So entities are basically real world objects. Okay. They are unique and distinguishable. Okay. So it could be any person, thing, or place, right? So some examples of entities relevant to a problem domain, let's say in our university problem domain. So some example of entities will be students. Try to make it a habit to capitalize the name of your entities, okay, as much as possible. Then you have professors. Then you have staff. Then you can have buildings within the university. You can have, let's say, resources, classroom resources, something along those lines, and so on and so forth, right? So any real world object will be represented as an entity within a data model, okay? Thereafter, we have attributes, okay? So attributes are basically features or properties of an entity, okay? So if you remember, when we were discussing some basic terms, we said that field, what is field in a file system, is known as attributes in a database system, right? So that is where the attributes aspect is coming from. It is a character or a group of character, which could be alphabetical or numeric or a combination of both, that is used to describe the data that is being stored there, right? And the data that we're trying to store is in the form of an entity, right? The real world objects that we are trying to model in our database environment, right? Or through our database design. So each of these database entities or these data model entities will have their own features or will have their own properties, and that is what attributes represent, okay? So some examples for attributes, let's say for student, is going to be your student ID. And the second habit that you should make is any attribute that you specify, you should follow it up with a prefix of the acronym or the full name itself of the entity that that attribute defines. So you can have student ID, then you can have student name, then you can have student address, then you can have student phone, and so on and so forth, okay? So stuff like that, you get the idea. So you will have to understand, based on the client requirements, that what type of data is being stored, right? And this is the type of data that you're trying to store for the given entity, right? And that is what is going to give you an idea of where do you go from there, like once you get the client requirements, okay? So after entities, we have relationships, right? Which is the nature of interaction between entities. Okay. So of course, not all entities will interact with each other, but most of your entities will have some level of interactions with each other. So some examples of relationships could be something along the lines of professors advises student. Okay, so this advices is a relationship between two entities, which is professor and students. So this is what a relationship is basically trying to establish, is what is the nature of the interaction between these two entities. So when you specify that, when you specify a relationship, you have to give two things. Okay, So the first one is the relationship label. Okay, that is, what is the nature of the interaction? And then the second thing is the relationship type. Okay, so the label is pretty simple. As long as you understand how the two entities interact with each other, you can provide a label to each other, or between those between the relationship of those entities. Okay, but there are three different types of relationship that you can have between the entities. So the first one is 1:m. That is, one unit of a given entity is associated to m different units of the other entity. Okay. The second one that you can have, the second relationship type, is 1:1. That is, one unit of a given entity is associated with only one other unit of the other entity. And then the last one that you have is m:n. Okay, where m units of a given entity is associated with m units of another entity. So let's look at some examples of these relationship types before we revisit the last component, which are constraints, right? So the topic that we are asking, or we're going to discuss, is different relationship types. Okay. And we said that the first one is 1:m. So this is a way of representing 1:m. Given the type of data model that you adopt, the graphical representation of the relationships are going to vary. Okay, so we are not going to go into that right now. We will do that when we go into chapter 4, which is entity relationship modeling. The second one we spoke of is 1:m. And then the third one is basically m:n. So a thing to note is that this has a direct physical implementation. This also has a direct physical implementation. Remember, all of these topics that we're discussing right now, yes, it will go into the design, but that design needs to be converted into an implementation. So when we say it has a direct physical implementation, that means that there is a straightforward way of projecting this relationship representation into the software implementation. So now this is a logical representation. So keep this in mind later on as we progress towards the implementation of database designs, and we discuss specifically with respect to the relational data model. We will see why we are saying that 1:m and 1:1 has direct physical implementations, whereas m:(n) is a logical representation, requires tweaks to implement physically. So this is just a quick remark that you have to keep in mind. So now let us discuss some examples, different types of examples that falls into these relationship type categories. Okay. Try to think of it yourself first before you look at the examples by yourself, and see if you can reason with the nature of these different relationship types that we are going to discuss. Okay. So 1:m is pretty straightforward. One unit or one entity instance of a given entity is associated to m different entity instance of the other entity. So that example we already discussed. So here that example will be that of professor advises student. So what this is interpreting as, or what we can interpret this as, if it falls within the 1:m student category, is a given professor can advise multiple students. Later on, when we choose a specific data model, you will see that when we are interpreting the nature of the relationship between two entities and we express it something along these lines, we have to specify both the lower bound as well as the upper bound. So that means a given professor can advise at least 0 or more students. Okay, so a professor may or may not advise a student. So you can also rewrite that and say that a given professor, or a professor, given sounds a bit weird. So let's just say a professor may or may not advise 0 or m number of students. Right? So we need to provide an upper bound, and the upper bound is always going to be m. But the lower bound can vary, right? It could be 0 number of students, it could be 1 number of students, it could be 3 students, depending on what is the organization policy. So what is really important here to pay attention to is a lot of this database design depends on the policy or the client's requirements or the organization's requirement that you're following in order to generate your data storage unit. Okay. So always remember, what are you trying to model? That is the most important thing that you can ask yourself. What are the requirements? Okay. Because this is not mathematical algorithms. Database design is very conceptual, but it is also very subjective. So given the nature of the problem that you're trying to solve will dictate many of the different techniques that you apply. Okay, so you have to be flexible with regards to that aspect. Okay, so here we can say professor is 1 and student is m. Similarly, what will be an example of a 1:1 relationship type within the university domain? So here we can say a professor chairs a department. Okay, so there can be only one chair for every department within the university, right? Any department, that is. So this relationship is 1:1, right? However, the reason why labeling is important is because if you now switch the nature of this interaction, then you can generate a completely new relationship and relationship type between the same two entities. Okay, so that means alternatively, so this is not with respect to 1:1, this is just to show that there can be multiple different types of relationship between two entities. So what we're trying to say here is two entities can have different context of interaction. So the example for that is if we do department employs professor, then now suddenly this relationship is 1:m, because a given department can employ multiple professors. But however, if the nature of the interaction is chairing or being the head of the department, then it suddenly becomes 1:1. Okay. So now finally, an example for m is to n logical representation. So what will be a good example of m is to n representation? That is, m units of a given entity is associated to n units of another unit as an entity. Okay. So the example for that is basically going to be student enrolls courses or register for courses. So here it means a given student can enroll for n number of courses, and a given course can have multiple students. So that is where the m is to n nature is coming from. Okay. So one thing to keep in mind when we are talking about relationship types. So this is basically a remark or a note on relationships. So this is known as what is called the bidirectionality of relationships. Which is saying that given an entity 1 and a relationship between entity 1 and entity 2, whatever relationship that you are specifying in one direction, that relationship in the other direction must also hold. So we are saying, and we can take the most recent example that we talked about here, is when we say a student enrolls in a course, it has 1 to n. Okay. However, a course has students is also 1 to n, and combining these you have m is to n. Another example would be that we talked about here, where professor advises student. Then you have professor advises student is 1 is to n. Okay. And then the bidirectionality states that student advised by professor. So here m is to 1 must hold. So if in one direction the relationship is 1 is to m, then in the opposite direction m is to 1 must hold. Now it is kind of counterintuitive to discuss this for 1 is to 1 relationships, because if in one direction it is 1 is to 1, then in the other direction it should also be 1 is to 1 for the same context of the relation, not changing the different context. Okay. But what is important and what you need to read between the lines is that for this particular relationship type, which is 1 is to n, if in one direction of the relationship you have 1 is to m, then in the opposite direction m is to 1 must hold as well, right? So a student should be able to advise, or the student should be advised by only one professor and not m professors. Okay. However, if you notice this interaction here, you will see that the nature of the interaction does not hold. The bidirectionality does not hold. But it is still a valid relationship type. And that is where the fun of m is to n relationships begin, right? So this is also one foreshadowing of why we said that m is to n, 1 is to m, and 1 is to 1 have direct physical implementations, and m is to n is a logical representation. Because bidirectionality in a straightforward fashion does not hold for m is to n. So we have to eventually break it down to make sure that bidirectionality is preserved. Whereas for 1 is to 1 and 1 is to m, you have to make sure that whatever relationship that you are establishing, in the context of that same relationship, in the opposite direction, the opposite relationship type must also hold. So to recap, if professor advises student is a 1 is to m relationship, then student being advised by professor must be m is to 1. In the same context, that is in the context of advising or being advised, not changing the context. Okay, and when I say changing the context, then I'm referring to this example here. It is a relationship between the same two entities, but the context is different. One is talking about managing the department, and the other one is talking about the department employing the individuals. Okay, so you have to keep that in mind. And then finally, coming back to the last building block that we have, constraints are basically, well, constraints that you place on your data, or you can simply say restrictions to be placed on stored data. So these are pretty straightforward, right? So in the university domain, your constraints could be for a particular attribute. So typically if it is placed on the data, then it will be placed majority of the times. There will of course be some exceptions on the attribute itself. So you can have the student GPA being within 0.002 to 4.00, or if your scale is different, if you're in Europe, then it could be between 6.00, right? And so on and so forth. So these are some of the design restrictions that you can place on your data as well through your design, right? Either through your design, and later on you will also learn that there are some restrictions that you cannot place through the design itself, right? You have to place them specifically through implementation when you are developing your queries and you're writing them, right? So these are some of the basic building blocks of data model. So most of them would be similar across what different data models that you apply, but how you represent them is what is going to change when you are going to formalize the data model and select a particular data model and then go on with it. So the next topic that we have are basically, let's call it 2.2. Okay. I don't remember if we gave a separate topic number for business rules. So let's just say business rules. Okay. So business rules are basically transforming the unstructured end user requirements as well as, and you can add as well as, the organization requirement into something more concrete that clearly identifies and describes how data will be generated, managed, and consumed. Okay. So this is the reason why we want business rules, and what business rules are. So the definition for business rule is basically, so this is a definition, so this has to be accurate to the keyword that describes a business rule, and you cannot make up your own stuff. But as long as you convey the idea, that is good enough. So it is basically brief, precise, and hope I don't get it wrong, ambiguous description of a policy, procedure, or principle within a specific organization. Okay, so this is like the more informal definition, and this is what the process of business rule is going to help us achieve. Okay, because when you are talking to your clients, or when you're talking to your end users or your internal users, they will all going to specify that, hey, they want to have this data in store, they want to process the data in this particular format, and so on and so forth, right? So you need a structured way to represent all of this information that you're gathering from your clients, right? And that is where you take the aid of business rules. So you establish that clearly, and you get it done. Okay, so it kind of standardizes the notion of the view. So as we said, that data model bridges the gap. You first generate business rules and then transform those business rules to data model. So just like data model bridges the different views of data from different parties that are involved uh, in the process of database design, business rule is also like a prerequisite or a pre-step to the design of data model itself. That is, you give structure to the collection of the requirements analysis that you have done by, let's say, interviewing your clients, interviewing different units of your organization who would like to interact with the database, talking to the different application developers as to like what kind of application they are trying to develop and how that will interact with your database. And then you develop your business rules. So once you do that, then you can generate your data model from your business rules thereafter. Okay. So what you have to keep in mind when you are transforming business rules into a data model representation. So what you have to keep in mind is this is all text. It still is unifying all the different parties that are involved in a structured fashion and creating this one single view of your database design, right? And this is basically your graphical representation. So that is the difference. That is what we are aiming for. Okay. So anything that is a noun in the business rule statement becomes an entity of data model. And anything that is a verb in the business rule statements becomes a relationship label of your data model. Okay, so that means, and it also specifies relationship type, and of course in a bidirectional fashion. Okay, so that means if we say that a business rule typically will be of the format you will have point 1, which will say a professor from the CSE department will advise multiple students. Okay, and then to ensure the bidirectionality, we will say students enrolled in the CSE department can be advised by a single professor. Okay, so of course before this we have to add multiple students enrolled in the CSE department can be advised by a single professor. So this will represent the interaction between two or more entities, or even within the entity itself, right? So here we can say that we can take the nouns, which are professor, students, professors, and convert that to entities. And we can say professors and then student. Okay, and then we will take the verb, which is advised or can be advised, will advise and can be advised, and then transform that to a relationship label. So given the direction of the relationship, we will express our relationship label. So we can simply say advises, and then we can say a professor, multiple students. Okay, so 1 is to m, and then we also have to ensure that in the reverse direction within the same context it is m is to 1. So multiple students can be advised by a single professor, right, which is m is to 1. So this is how a pair of business rule transforms into a data model representation. Remember, every data model representation should have a pair of business rules to ensure the bidirectionality. This is a very important note because you will have assignments and you will be doing your projects where you have to specify your business rules. So, important remark to keep in mind is a given representation of in a data model, let's just say in a data model, will be expressed using a pair, and this is very important, of business rules. Okay. Later on, we will try to do a more hypothetically practical example where we will look at some of the client requirements and we will try to translate that to business rule and then generate a graphical representation from those business rules. But we would want to go to chapter 3 or 4 in order to do that, because then we will actually formalize or establish what data model we are trying to use, and then the representation will be kind of structured rather than using some generic ways of representation. But the first and foremost thing, and the most important thing within the realm of business rules, is to always remember that for every interaction in the data model, for every graphical representation in the data model, will always be expressed by a pair of business rules, not a single business rule, but a pair of business rules, which will take care about the of the bidirectionality of the interaction. Okay, and of course, again, so that concludes the importance of data modeling, the purpose of data modeling, the basic building blocks of data modeling, and then finally, what are business rules, how are they expressed, and then the typical way of transforming a business rule into the graphical representation of a data model. Okay. So I'm going to conclude this video now, and let's say end of part 1. So there will be another part 2 video where we'll be discussing the last 2 topics, which is evolution of data models and then different degrees of data abstraction. So I'm going to see you all again in the next video for this particular chapter. Until then, take care and stay safe.